All right, thanks, Barbara, and thanks for the invitation to speak in this session. So my talk today is actually going to focus more on some of the observations we've found of these increased earthquake rates. And the talk following mine, given by my colleague Bill Ellsworth, is going to focus more on the hazard implications. So by now we're probably all pretty familiar with the observation that the earthquake rate in the CEUS has increased significantly since 2009. This figure from Bill's paper in 2013 shows the cumulative number of magnitude 3 and higher earthquakes from 1970 through 2013, and you can see that the rate is pretty much constant until about 2001 or so, starts to increase gradually, but really the sharp uptick occurs in 2009. You can also see that in this figure here on the right, which is just showing the binned yearly rates of these earthquakes from 1973 to 2014. And the red line here shows the expected rate based on the earthquakes that occurred before 2009, with the dashed and the dotted lines showing the 95 and 99% confidence limits of that rate. And you can see that the annual rates following for 2009 onward are all significantly higher than that expected rate by factors of 2 to 4. But the earthquake rate isn't increasing uniformly across the entire mid-continent. It's really only limited to a few geographic areas, which happen to be areas where oil and gas production are occurring. So to illustrate that, let's again take a look at this cumulative number plot. So this is now zoomed in, looking at 1995 through 2014, with the dashed line here indicating 2009. So let's start taking out earthquakes that are occurring in places that have been identified in the literature as having induced seismicity. And let's start with Oklahoma, for example. And so right away, if you take out the earthquakes in this box around Oklahoma, you can see that that rate increase drops off significantly. Then let's remove the earthquakes in Guy-Greenbrier. You can see that that again flattens out this rate increase. And then we can remove earthquakes in the Raton Basin here on the Colorado-New Mexico border, which flattens it out more. And then earthquakes in Cogdell, Texas, and by this point you can see that we're pretty much more or less at this sort of pre-2009 background rate. And then we can go ahead and remove some of these smaller sequences in the Dallas-Fort Worth area, Timpson here in eastern Texas, Dagger Draw in New Mexico, Paradox Valley in Colorado, Fashing, Texas, and you can see that this pretty much gets us back to this background level. So this really suggests that these new earthquakes are all tending to occur in these areas that that have significant oil and gas production. But we've also developed a statistical method to objectively identify areas in the US that have seen significant increase in seismicity. And so we do that by starting out with the earthquake rate model that was developed for the 2008 version of the National Seismic Hazard Map. So this rate model is based on a spatially smoothed and declustered catalog of past seismicity in the CEUS. And so we can use that model to predict the expected number of earthquakes we would have thought would have occurred from 2009 through April of this year. And that's what I'm showing here on this map here, color-coded with the warmer colors indicating the higher expected numbers. So then we can compare that map to the map of the actual numbers of these earthquakes that we observed, and so that's shown down here on the same color scale. So right away you can see that there are earthquakes happening in places that weren't really expected to have a lot of seismicity prior to 2009. So then we can take these two maps and then compute the probabilities, the Poisson probabilities of seeing these number of events given this earthquake rate model. And that's what I'm showing on this map here on the right. So this is now showing the probabilities of getting these observed numbers of events with the lowest probabilities in the warm colors here. And so, so basically the low probability areas are the areas that are seeing significantly higher numbers of earthquakes than the 2008 model would have predicted. And so we've identified 5 areas that have significantly increased seismicity at the 95% confidence level. And these are Oklahoma, the Raton Basin, the Dallas-Fort Worth Azle area in Texas, Cogdell, Texas, and then finally Paonia here in Colorado. Now with the exception of Paonia, which is likely related to underground coal mining, all these other areas, again, all occur in oil and gas producing regions, and all have been suspected of having induced seismicity in the literature. So let's zoom into Oklahoma, which is by far the largest contributor to the CEUS seismicity increase. So if we take that statistical method that I described in the previous slide, we can apply that to the earthquake catalog in Oklahoma to identify these areas of increased seismicity and look at how they evolve over the years from 2009 through 2014. So these colored areas represent sort of the contour of the extent of these areas of increased seismicity. So you can, and I should mention that the dots are the earthquakes, magnitude 3 and higher earthquakes from the Oklahoma Geological Survey catalog that help define these regions. So you can see that from 2009 through about 2012 or so, the area of increased seismicity is really concentrated in the central part of the state. So this includes areas like, so things like the Jones sequence, for example, the Prague sequence. It's all pretty much concentrated here. But then starting in 2013, we see an expansion both to the south and also to the north of this area of increased seismicity. And particularly this expansion to the north continues through this year. And this area to the north, up near the Kansas border, corresponds with the Mississippi lime play, which is a carbonate formation being exploited for oil and gas. If we just focus on the past couple of years and instead look at 6-month intervals rather than yearly intervals, again, you can see that you can see this gradual migration to the north of the seismicity from 2012 through 2013 and earlier this year. But interestingly, over the past 6 months or so, which are the area of increased seismicity seems to be concentrated in this region just a little to the south of the Mississippi lime play, which could be related to processes that are activities that are going on in the Hunton Formation rather than the Mississippi lime. So given that we have these kinds of, we have the ability to map out these kinds of contours and look at how these areas are evolving over space and time, we can then compare the space-time evolution of the seismicity increase to the space-time evolution of industrial activity. And one metric that I'm going to show here of industrial activity is the number of wells being drilled or being completed in Oklahoma over time. So what I'm showing here are yearly maps with the colors representing the number of wells completed in each Oklahoma township. So the gray colors are wells, are numbers of like 1 to 10 wells completed per year, and then red is more than 40 wells being completed. So basically these are drilling density maps, and going from 2008, 2009, all the way through 2013. Now, plotted on top of these maps, I'm showing the seismicity from the year following the well completion. So for example, this top figure here is showing the 2008 well completion map. Plotted on top of that are the earthquakes that occur the following year. And then the red line here represents the contour of that area of increased seismicity that we identified. And so, interestingly, you can see that in 2012, the number of well completions sharply increased here in this area of the Mississippi lime play up near the northern border. And then you can see that the seismicity actually follows that the following year. That trend continues in 2013. Again, there continues to be a large number of wells being drilled up in the Mississippi lime play. You can also see an uptick in the activity here associated potentially with Hunton dewatering. And again, you can see that the seismicity is actually following, also seems to follow the industrial activity here. So this suggests that at least in the northern part of the state, the seismicity does indeed seem to be following, sort of tracking some of these well completions. Another way of looking at that is by taking a look at the cumulative number of earthquakes that have occurred in Oklahoma since the year 2000. And if you just focus on the black line, this is showing the earthquakes over the entire state. And then we can compare, well, just by looking at that black line, you can see that besides the obvious change point that occurs in 2009, there's also a change in slope that occurs somewhere in mid-2013, and then another one that occurs in at the early part of this year. And you might think, well, maybe the seismicity is just accelerating. But in fact, these change points are due to the expansion of the activity into these new parts of the state that hadn't really seen very much activity before. And you can see that because, so if we take this polygon, for example, box A, which is roughly in the area of the Mississippi lime play, the seismicity rate in this box is shown by the blue curve down here. And you can see that it's actually really very quiet until things start happening in 2013. and then really start picking up 2014. And then you can see that also in this box B, which seems to be a sort of distinct cluster from box A. The box B curve is shown in gold, and you can see that it's pretty much quiet even through 2013 and just really starts to ramp up in the early part of this year. If we look at the number of wells completed by year, and just from 2000 and until 2014, the bars in the black are the number of wells completed in these two polygons. And you can see that in the year or two leading up to these seismicity increases, the number of well completions also increased. And in fact, in both years, over 1,000 wells were completed each year in this general area. So taken all together, these observations seem to suggest that there's a link between these seismicity increases in Oklahoma that we're seeing and oil and gas production, either directly or through the sort of the associated wastewater disposal in these plays. So given that we have all these new earthquakes occurring and that they're potentially induced, should they be treated in some way differently than natural tectonic earthquakes in our hazard assessments? There have been a lot of previous studies to suggest that induced earthquakes might have different characteristics, might have, for example, different magnitude frequency distributions than natural earthquakes. A paper by, for example, Bachman and others observed that earthquakes that occurred during times of injection had higher B values, for example. Another way they might be different is that they might have different clustering characteristics. And so these characteristics are important to consider because usually time-independent hazard computations assume that these things remain constant over time. So if there are, in fact, changes in these parameters, they might be causing changes in hazard that may or may not be entirely accurate. So let's start off by taking a look at the earthquake size distribution, magnitude frequency distribution in the CEUS catalogs. So I'm showing here the frequency magnitude distribution for the ANSS catalog, and then the National Seismic Hazard Map catalog. And the black dots here represent the earthquakes that occurred before 2009, and the red dots here are the earthquakes that occur after 2009. And so you can see that in both catalogs, there is a statistically significant formal increase in the B value from about 0.8 or so to 1. But actually, the amount of this increase differs between the two catalogs. And in fact, differences in both the reported magnitude types and magnitude estimates in these sort of larger scale catalogs in space and time actually make it difficult to determine whether this increase in B value is real or whether it's just an artifact of the different catalogs that are being used. So that's still kind of up in the air. But we focus instead on the earthquake clustering. A previous paper that we did that came out last year observed that there seemed to be a significant increase in the clustering that occurred in Oklahoma and Arkansas starting since about 2009. And basically what we did was we fit a statistical model, the USGS model, to the earthquake rate changes in these places. And we found that in order to explain this kind of earthquake rate increase, you needed to have not only a change in sort of the background rate of earthquakes, but also a change in the aftershock productivity. In fact, the aftershock productivity increases by factors of 4 to 10 in these places. And this is something we don't really observe for when we try to do this kind of modeling with natural earthquake rate changes, so natural earthquake swarms. I mean, this is basically saying that a magnitude 4 earthquake that happened after 2009 triggered far more aftershocks than it would have triggered had it occurred before 2009. So this led us to suggest that this is perhaps an indicator of induced seismicity. The other thing that we observed was that the inter-event distances in Arkansas tended to decrease for earthquakes that occurred within about 6 kilometers of a wastewater injection well. So this figure here shows a cumulative distribution of inter-event distances, with the red symbols here showing the distribution for the earthquakes that occur within 6 kilometers of an active well. And you can see that these distances are much smaller, so these earthquakes are much more spatially clustered than the earthquakes that had occurred either before, after, or far away from active injection, which are represented by these other distributions here. So again, this suggests that a change in clustering might be indicative of injection-induced seismicity. But these changes in clustering aren't just limited to Oklahoma and Arkansas. In fact, we can observe it throughout the entire CEUS. So this table I'm showing here is the fraction of each of these CEUS catalogs that are identified as being clustered events, so as either foreshocks or aftershocks in sequence. And these are just using two different methods. But basically what you can see is that before 2009, the fraction of these catalogs that were aftershocks or foreshocks were about 10 to 15% or so. After 2009, that fraction increases significantly to numbers more like 40 to 60%. So to give you some comparison, some idea, that's pretty much the fraction of the California catalogs that are considered to be clustered events. So this is really a significant change for the CEUS. If we remove the earthquakes that are all sort of in these induced seismicity areas, then you can see that that increase disappears. And then if we just only remove the Oklahoma earthquakes, that increase remains. So this increase is not just because there are more earthquakes occurring in Oklahoma. So given that we have all these new earthquakes occurring, given that they're likely induced, and they do have some characteristics that seem to indicate that they might be different from natural earthquakes, what kind of impact can we expect them to have on our hazard assessment? Like as I mentioned before, Bill is going to talk about the hazard in greater detail, so I'm going to simply end here by saying that simply increasing the earthquake rate in the region is automatically going to increase your hazard. But the amount of that increase is going to depend on how you treat all these new earthquakes and what assumptions you make about the kinds of behavior that they have because they are induced. But really, whether or not these earthquakes are natural or induced, they really are going to affect our hazard in ways that really aren't accounted for in our current hazard assessment practices. So I'll stop there and leave my conclusions up and there for you to read. So thank you.
Time for a few questions. Well, I have a question. I'd like to know, a lot of your, that was a really nice summary of how clear it is that things have changed and many tools that you can use to assess that the situation has changed. How quickly is it possible to evaluate that things have changed so that there can be an adaptation by regulatory agencies, like things moving into northern Oklahoma? How long a time frame with the catalog that you have do you need?
So I guess the answer to that would be that it varies. For the kinds of statistical models that I showed, really you need to have a good baseline in order to establish that the changes occurred. And the problem that we face in a lot of these areas in the central and eastern U.S. is that because of the lack of dense instrumentation, we really don't have that good baseline established. So it's hard to say exactly when things start changing right away.
But your study, you could show over 6 months. You showed over half a year.
Right, but those were all, and that was all compared to sort of the 2008 rate model. So.
Another question?
If you go back to that slide where you took out all of the active areas and you showed the rate going back to 2000, I seem to notice a little bit of slope change at about 2002. Can you explain what's going on there? Scope array starting to roll out across the central U.S.?
I'm not entirely sure. I mean, you'll note that this is around the same time that there's actually that increase that was in Bill's plot in his science paper. If you go back here, this also shows that the increase starts at about 2001, but and there are sequences. For example, the Raton Basin. I think the rate increase did start sort of around that time. But beyond that, yeah, I'm not exactly sure what the cause of that is.